Hi, my name is Hugh Sanderson and I'll be talking about the HXCPP magic. There are two definitions of magic here. First is from the dictionary and the second is from the Haxe website. Since I haven't worked out how to use supernatural forces, I'm going to be using the second definition. Magic is mixing the Haxe code with the non-Haxe code to take advantage of the native system. There are a few tasks you will probably need to do when mixing native and generated code. The first is to add include paths and libraries to the build system. This allows the compiler and linker to find the headers and the libraries required to build the executables. Then you'll either need to inject code directly into the generated output using the untyped keyword, or to create extern definitions to tell the Haxe compiler to generate placeholder calls directly into the native code. The first thing you'll need to do when linking against native code is to hook into the HXCPP build system. No build system is magic. All they need to do is provide the correct linker and compiler flags along with a list of files and dependencies. There are other systems that do similar things, and none of these is magic either. The HXCPP build system attempts to solve the build problem as explicitly as possible by simply generating the list of files and dependencies and using a standard set of flags in the toolchains provided with the HXCPP HaxeLib for all supported targets. There are well over a dozen of these targets, and I think this shows the effectiveness of this solution. A custom solution was chosen mainly to avoid excessive dependencies on things like Java or Python, and the current system requires only Nico, which all Haxe users have installed. The build.xml file is generated and run by the Haxe compiler, but you can run the build system directly using the HaxeLib run command from the same directory as the generated build.xml file. This allows you to quickly iterate with direct changes to the build file without needing to change the Haxe source code. From here, you can also edit the generated CPP code, and this is a great way to explore the structure and the syntax of the generated output. Once you run the Haxe command again, your changes will obviously be overwritten. Build.xml files can also be used with non-generated projects, and this is a great way of building libraries and NDLLs that are compatible with the Haxe-generated executables on all supported targets.
You can control the building of the build.xml system using a couple of techniques. One is with environment variables. Now, depending on what shell you're using, set, zm, export, all fairly similar. Or you can make the permanent changes in your either .login or by setting the environment variable on your Windows control panel. These are kind of making permanent changes rather than a sort of a per project or per session change. You can also use defines to control some of the build outputs and the build parameters. If you're using the Haxe compiler, you add a define on the command line with a -d space, then the define name. For all other things, there's no space. So HaxeLib run, there's no space after the D. That's just a little gotcha for new players. Another possibility is that you can set the defines up in the HXCPP config.xml file, and this would be sort of machine-specific setup rather than project-specific setup. For instance, you may have your Android SDK installed in one directory on machine A, but in a different directory on machine B. By setting it in the sort of the per machine XML file, means that you don't have to worry about moving stuff into the same spot all the time. And a new facility we've added is the ability to pull in a toolchain/setup.xml file from within your Haxe class path. Typically, your Haxe class path will get set with the -lib command. So you could have your own toolchain, compile your Haxe code with the -lib toolchain. And that will go in and look for this setup.xml file and use that in preference to the one that comes with this HXCPP compiler. And from within this, you can set variables or pull in paths from elsewhere, and you can completely change the whole toolchain file. If you want to make your own, it's probably good to start by copying one of the standard HXCPP ones and just modify some of the flags. And I think this will be useful for things like if you wanted to write like a cross-compiler for your particular system and it's not supported by CPP, you can support it with a HaxeLib, and I'm hoping to get some user contributions on HaxeLib for different compiler chains. So once you've got your build system set up, we'll look at some of the simple things you can do to integrate external code. Most of the external code is introduced with the untyped keyword, which just instructs the Haxe compiler to trust you. Whatever's following is the correct type. Don't worry about complaining about the wrong type. So it just skips the type checking component, but you still have to type in valid Haxe code as far as the parser is concerned. You can't just start using, sort of string indexes or anything like that. This often is used within the current CPP runtime to link to some of the global functions that actually do the work of the back end, and is used in conjunction with the global command. The global command just puts things in the top level namespace. So in Haxe, you can't have a static function that is not part of a class, but if you've provided external static functions, they probably aren't part of a class. So if you use the global sort of pseudo class, it just puts things in the top level namespace. This little example here, you can just hook straight into the Windows message box command, and it just happens to work because the Windows.8 is included by default on Windows. The 0 actually turns out to be the null pointer, even though it's written as an integer, and the hello will auto-cast to a const char star. So that's just some of the things you can do with the global pointer. Mainly this is for internal stuff. If you look in my header files, I've got a whole bunch of things called underbar, HXCPP, blah, blah, blah. And that's what actually does most of the work in the runtime. The last one is the CPP pseudo function. It takes a string and just inserts that string verbatim into the generated output. As a string, it means you can pretty much write whatever you want, and the Haxe compiler will parse it, but once you get to the C compiler, it'll complain if you've got something wrong. And because it's a string, anything goes, but you've got to watch out for instance, if you use a variable name, the Haxe compiler will rename some of your variables as far as the CPP code is concerned. For example, if you use a keyword as a variable name, it'll stick an underbar on the beginning of your variable name. And if you use the same variable name multiple times within the one scope, they'll have a little index appended to them. So, and same with an inline function. Once you inline function, the name of the argument disappears, and it no longer works. So there are a few issues with the CPP command, but it's not bad one if you just need to jump in and put a little hook to something in the code. Another thing that's been added recently is the extensions into the CPP package in the Haxe standard library. I've added a native array class, which you use with the using directive. And when you use that, it imports some extra functions into the array class. So you get the unsafe get and unsafe set functions, which will do the array index dereference, but not do the bounds check. So these will actually be reasonably faster if you put them in a loop. But as the name suggests, you want to use them at your peril. There's also array 0, which will set everything to 0 or null or false, depending on the array type. And there's a blit function as well for copying sections of arrays. The string class gets this cstr function, which just returns the native const char star pointer, which is mainly useful for passing it off to external code. But I'll get to the pointer class in a little bit. You'll notice here I use the .@1 function, which will take the 1th element of that array, being the letter E, and actually return the char 1, which actually will be the ASCII code of the letter E. So that'll end up being an integer. The float 32 has been added after some badgering by the 3D guys. It's the 32-bit version of the float. By default, CPP will use 64-bit floats. There is a switch that you can actually switch all the floats over to 32 bits, but that's probably not widely used. And if you use the 32-bit float just when you need it, it could work out better. You can see here the size of operator returns 8 for a standard float and 4 for the 32-bit float. You'll also notice this CPP syntax here with the brace, zero brace syntax will do C# style substitution of the first parameter into that string. And this is something that was contributed to me, and I think it's actually quite useful. And in fact, in some ways, it gets around the issues that I was speaking about with variable substitution, since the expression actually gets split up either side of that bracket 0 and then concatenated together. It could actually work out better for you. There's also some integer lower precision types, uint8, 16, 32. Well, 32 is the default. 64 has been added as well. I'll get to that in a minute. It's not perfect at the moment. So these are ready to use in your own projects. It's not that much point saving space by using a uint8 in anything other than an array. So level 2 magic is the old magic I used to have in there, which is the meta magic. And this lets you inject code into different parts of the output code. Now, you have to know a little bit about how the C++ class files, header files and stuff are structured in order to get the code into the right spot. But broadly speaking, if you need to put a variable into a class, you will need to put it into the header class code. If you need to put an include into the generated code, you need to put it into header code. And then there's header namespace code is maybe not so much used. And then the CPP file code goes at the top of the CPP, and that would be traditionally to include an external header file. And then the CPP namespace code, you need to put it there in order to reference global variables within the class namespace. So you really need to know a bit about how where the particular functions and things should be put in order to be able to use that correctly. There was also some metadata that you could put on a function, but this is now largely redundant because the CPP directive actually works just as well. But finally, the build.xml metadata is something that you'll probably want to use with your external classes. And what this does is injects XML fragment into the generated build.xml. And this is really useful for two things. One is adding an include path to the compiler, so that when you include, say, if you wanted to include wxwindows.h, it would need to know the base directory to include that from. So you'd inject that include path. And in this particular case, I've added the winsock32 library to the output when you use the std static library. So that's adding a link library to the generated output. I use this particular example is taken from the static std class, which allows you to link the standard C++ std.ndll in statically instead of dynamically. You can just import this class and it will do a static link against the std static. You also know I've got the keep metadata on this class. You probably need that too because there were actually no real functions in this class, and the dead code eliminator may eliminate your class otherwise. Now, the build.xml syntax here is the same syntax as goes into the build.xml file, but you don't really want to try to write too much code inline in the Haxe code because you run into issues with quotes and double quotes, and there's quite a few things that can go wrong. So easiest is really just to include a single file and put all your stuff in there. So this is what NME does when you link statically. It includes the HaxeLib NME/lib/NME link, and then I can put whatever I want in there, add libraries, make things different for different targets. This is build.xml syntax with the $HaxeLib NME here. That just looks up HaxeLib and finds the path. So there's a few things with the build.xml file syntax that can help you there. So external magic. This is the kind of newer stuff and probably the better stuff to get into. I've added this new CPP pointer class. Now this effectively is like a void star pointer that you can sit in your classes or in static member variables or class variables. They're typed, so there's a template parameter here of what the pointer actually points to. And you can do things with the pointer class like the .value property actually dereferences the pointer. There's @ which is like the array index, add for pointer arithmetic, less than for comparing pointers. It's designed to be worked with an external class, which I'll get to next, but you can also use it actually on your Haxe member variables themselves. But you have to be careful here because the pointer won't hold a garbage collector reference, so it's quite possible that the data that you're pointing to might actually move while you think you're pointing to it. So there are a few things I'll go over in order to ensure that doesn't happen. The easiest way to make sure that doesn't happen is to not run anything that uses garbage collection while you are actually holding one of the pointers. So treat a pointer to a Haxe variable as only a temporary thing that you're using, which you'll dispose of before you do anything with garbage collection. There's also the CPP function, which is a function pointer. And at the moment, you can take the address of a static function, which is the traditional C-style function pointer. You can't use a closure or a member function pointer because they require extra data. Traditionally, the C guys get around this by just making the first parameter to the static function the actual class that you want to work on. Again, this is probably more useful for external interactions and the finalizers, which I'll get to later, but it's there as an option. So if you have a look at this little example here, I've created an array. I'm using the pointer to array element, the 1th index of that array, and that's an int pointer. Now Haxe knows that's strongly typed as a pointer to int, and then if I trace the .value, it dereferences that integer value, being the number 2 in the array, and then I can add 1 to the pointer and dereference that, I get 3. So that behaves just like a pointer and is implemented effectively exactly as a pointer. So the extern class is now the, I guess, preferred way to interact with external classes is to write an extern class definition for it. So you can see here I've got an extern class definition for wrapping the std string class, and it's got some various metadata to go with it. First of all, include string. So anytime you use this class, the CPP codegen will generate an include for the string, which is required by the C++ compiler. Struct access, that's a new one too. Normally, objects in the CPP backend are actually smart pointers to the class and use the arrow operator, but if you use struct access, it'll actually use the dot operator to access the members, and that's probably more traditional for external data. Unreflective, that's added so that it will not take part in the get field by name, set field by name operations, mainly because they use dynamic access, and I've got no explicit cast here from the string to dynamic, so you'll end up with a compiler error if it tries to return one of these objects as a dynamic. There's also and native std string. I can't call the Haxe class std.string because the .string doesn't start with a capital letter, so the Haxe will compile. So what you can do is just use the std string class with a capital S, two capital S's in your Haxe code, and at generation time it'll actually just replace that with std : string. The constructors are also problematic. Like I can't use a new word in an extern class because it'll try to do a Haxe new on the class. So I use a little trick here where I create a static function called create, and in this create function returns a pointer to the std string, and I've used the native directive on this class to actually say that this function is called new std string. So when you go call create, what actually is generated on the output is new std string. And this way you can type up a constructor to work with your external code. And you can see here I've added the size and the find operators from the standard std string class. You can add whatever you want. You don't have to add them all. You don't have to... there is a slight leeway in the typing because you're really just telling Haxe what the typing is. It's not really telling C++ what the typing is. So, you know, if you wanted to put it int instead of short, it would still probably work. So here's the example, std string create, my string. In this case, std will be a pointer to this std string class, which Haxe knows about, and he knows that it's got a .size operator that returns an integer. So I go std.value, which dereferences it, .size, and it will return the number of characters that are in this string. And then the destructor, I call std.destroy. That'll end up calling delete on the pointer, on the string pointer, and that will tidy everything up correctly. Now, you can actually have a non-instance version, non-pointer version of the std string on the stack. So you can create a variable var x of std string, and that'll insert a non-pointer version of std string, and that'll still work. There's a problem though if you try to put one of those inside a member class, in that the constructor and destructor simply won't be called because the C++ classes actually just sort of get memory allocated and it gets set to 0, and there's no traditional destructor that goes with it. So you'll probably end up leaking code if you try to stick a non-pointer version of this on the stack. Oh, sorry, in a member class. So, you know, it is very much like a C++ pointer, which actually lets you do C++ pointer things. I'm not sure that's a good thing or not, but here's a little example where I create a float 32 number y. I take the address of it and I reinterpret it as a pointer to an integer, so it's no longer a float 32. And I do bitwise manipulation on the float 32-bit number, but using integer bitwise manipulation, which will affect the value in situ, and then retreat it back as the original variable as the float 32, and use this bit of maths that's been around for many years, and actually get a fast inverse square root approximation. So I'm not sure that this is what the graphics guys used to do, you know, many years ago. I'm not sure that you'd actually want to do this, but it's really just showing that the C++ pointer is the pointer class is very much like the traditional CPP pointer. Where you really want to use the pointer, it lets you access the data that you've allocated for within an NDLL. So if you allocate data in the NDLL using the alloc abstract class, that actually ends up in a Haxe object attached with a little pointer hidden behind the scenes. What you can do now is get at that pointer directly. So the first thing you do is define an extern for the type of data that's pointed to. It doesn't, as I said, it doesn't have to be an exact one. It really only needs to tell Haxe what the class has got. So it doesn't need to have all the variables in the correct order or the correct type or anything like that. You would then force the inclusion of the header file that does have all the correct information about the variable order and stuff into the classes that use your extern, and then include that. So you need to include that header library, which is the two steps. One is with the include metadata, but you'll also need to make sure that the include path is in the build.xml. You may need to add link libraries to your XML. For instance, if you're referring to like an external function on this data, you'll get an unresolved error if you don't add a library to your compiler, which involves modifying the build.xml. Although an alternative to that is one that I prefer and use wherever possible is if you make the functions in the external data all virtual, then you can call the functions directly from in the source code, and it'll use the vtable to get at the function pointer, which is a runtime thing, so you won't need to do compile time linking up the library. And this is also good if you've got two external DLLs that need to talk to each other. If you talk via a virtual function, then they don't actually need to link together at compile time. And then step 4 is that I've just spoke about. You extract the pointer to the data using the pointer from handle, and you can see here I've typed the pointer up with the my data parameter type, and then you can just use it by calling value sum func. So that gives you direct access calling or looking at the members of data allocated in an NDLL from CPP codes. There's no boxing, no extra type conversions. It's effectively calling straight into the code. So level 4 is necromancy, which is an important concept. Having created a pointer, and if it's a C++ pointer, and you've done C++, you know that you're going to have to delete that pointer at some stage. Now, one possibility is just to let the developers delete the pointer explicitly, saying, you know, you must call delete on this pointer if you allocate it. But there are some possibilities of using finalizers to delete the pointer if the developer has forgotten to. This CPP VM GC set finalizer attaches the finalizer function to the object. So when the object finally goes out of scope and it's no longer used, this function will be called. There are some problems with this, is that you can't use any garbage collection functions within the finalizer because it is already in the garbage collection finalizer code, and it would end up just blocking, waiting for itself to finish. So here you can see in this this fake destroy function that I've written here, I'm using CPP printf rather than trace, because trace would generate a garbage collection event, and then that would no longer work. You also notice that the type of the finalizer has to be void, and currently in C++ generated code, there's no such thing as a void function pointer, void function return. It's this kind of pseudo-void class that, this is because previously Haxe would let you return a value from a void function, which would just crash the C++ output. But I've added the metadata void to say, yes, this is really a void function. In the future, probably not too distant future, I think, you won't need this metadata. A void function will actually be the same as a CPP void function. So this finalizer gets called when the objects are no longer valid, but as I said, there's some issues. You can't really do very much in the destructor. What you could do is call delete, and that's probably the best thing. If you're just going to call delete, then it's fine to use this method. One of the other problems is that the finalizers can get run from arbitrary threads. So typically it'll be run from the thread that generated the new request that generated the garbage collection request. And this is particularly problematic for OpenGL, where you need to have everything running on the same the destruction of an object needs to be run on the same thread that created the object. So yeah, there are a few problems with finalizers. So as I said, if all you're going to do is just simply delete the object and move on, then you can maybe use it. The alternative is to use the zombie functions. This is mainly the CPP VMGC do not kill function. So you create a class, set it to be do not kill, which means that once the class goes out of scope, is no longer referred to by anything, it actually gets stuck on the zombie list. And then you can interrogate the zombie list at your leisure, anytime you like, to find all the objects that are no longer used by any other part of the code but the zombie class. Now, so in this main routine here, I loop over all the zombies and then decide what to do with them, destroy them. The good thing about this is that the loop is written by you at a time of your choosing, so it will probably be on the correct thread. And I guess a typical place to do this would be like on an on-frame enter in a gaming situation. You could loop through and see if any of the classes have gone out of scope. It's also possible to use this for debugging to track classes when their final reference is gone. And another good thing about using the zombie list is that you can reanimate one of these guys. So after he's dead, all his internal references are still intact, so you can just go back and insert it in another class, and it carries on as if it had never died. Not good for object pooling because there's costs associated with having the zombie list, but in other ways that's quite good. So just going over a few of the things from 2 years ago when I had my last talk, I had a long outstanding issue about the order of operations. C++ defaults to usually right to left when ordering of operations when no specific order has been specified, which is the exact opposite of what you want. I thought this bug was too hard and I didn't think I was ever going to get there. And I woke up one day and it was magically fixed for me. So I think I have Simon to thank for that one. That was pretty good. I said I'd track new features and new compilers as they came along, and we've done that. And also added like the new compiler framework, so hopefully that I can put some of the burden of supporting extra compilers onto other people. Some little improvements in garbage collection. I've added multi-threaded marking. On a desktop, you can run. I have it running 4 cores, which speeds it up pretty close to 4 times, but that's for just the marking phase of the garbage collection. There's also defrag moving operations in the garbage collector. They can be enabled and disabled with a define. I don't think we've had too much testing on that aspect of it, but if someone's interested, the code's all in there. And the integrated debugger now is a proper Haxe library, and it's been developed. Some things didn't work out quite as well as I was hoping. Strong function typing was something I had said I might like to look at. Currently, if you use a function pointer, it will effectively box all the input and output parameters. Now with the CPP function, it's a sort of a partial way of doing native strongly typed function pointers. There's still, it only works with static functions, but it might be enough for some of the external CFFI interactions where they actually all are static functions. And so it might solve some of the problems, if not all of them. Another thing I wanted to do was have specializations for some of the standard classes for ints, or integers and strings and doubles and bools that require boxing, and short-circuit the boxing with specific implementations, but I haven't got to that one yet. I've had a look at some of the Java implementations, and I might be able to steal some stuff from there. Using fake classes and interfaces for anonymous types. Again, this is something that I think would be a good performance win for people using the CPP backend. Currently, the standard way of fixing this is to not use anonymous types, but I think we can do something better there. I spoke about testing it with code coverage. I've sort of gone off that idea as a core CPP feature, thinking maybe macros would be a better way of doing that. And having some kind of graphical debugging memory, graphical view of how the garbage collection heap is organised, I thought would be interesting, but yeah, it hasn't been done yet either. So to the future, I'm still considering some of these things that haven't been done, the numeric templates and the fake classes and interfaces. One thing I've had in mind is concurrent GC, which will allow, it'll be slower on average for use, but hopefully reduce the pause time to as small as possible. Possibly enabled with some kind of define, and which I think would be good in a gaming situation to not get a stutter when, it's like a smooth scrolling situation. And probably some more native integration as ideas come up or as people start to use some of this stuff and have ideas of their own. And one way might be to steal other languages' extern definitions. There's plenty of scripting languages out there that have some pretty impressive libraries. I was thinking it would be nice to be able to hook into their extern definitions and use them directly in C++ somehow. And the flip side of that is to make the CPP NDLLs, like NME NDLL, available to some of the other targets. I'm thinking mainly Java and maybe JavaScript by using a sort of JNI, CFFI bridge kind of setup there. And there's some work to be done on Int64. At the moment, there are some abstracts in there, but if you have a dynamic Int64 and you add it to another dynamic Int64, currently you'll get an integer truncation. So there's a little bit to be done along those lines. So I'm just going to give a quick demo here on how some of this native integration can be done. Actually, this isn't my laptop, so I'm hoping it'll work. The NME exposes this image buffer class that you can get from a bitmap data object. So the standard NME bitmap data, you can actually get at the underlying C implementation of that and then use that directly from within the CPP code. It's got this stride and base, which is sort of standard image processing ways of accessing a kind of arbitrary image data. So you can see here I start with the source pointer, I add an offset. Now this offset would be like the row offset, which you can calculate from the stride and the row index. And that is reinterpreted, I think I'm missing a type here, but that's reinterpreted as a pointer to the ARGB type, which is another extern. Now the ARGB type is a struct which has an RG and a bytes in it. And then you can use the .r.g.b notation here. Now it would still be possible to do this without native integration because you could get the bytes as the integer array and then use bitwise manipulations to get at the individual fields. But with the direct inclusion of the header file, you can just access using individual components using the natural notation, and you're not losing any speed at all because it transfers to effectively exactly what you'd write in C++. All right. So this is the camera data here hooked directly into. I think I'm not very. So it's hooked directly into the bitmap data class. It's feeding in the camera and then using some basic image processing. It's using some basic image processing to track the RGB blobs and control the. Whoops, lost it. Yeah. So this is just sort of some of the things that you can do with some of the image processing things. And this is a direction I'm thinking of sort of pushing NME in, is some of the more image processing-y kind of. NME originally stood for native NICO media engine, and I'm sort of thinking of getting back into the kind of media aspects of it. So yep, that's my demo. Any questions?
Some questions about the GC of the HXCPP backend. Do you have some control over the allocation as well? How much to pre-allocate, or how big chunks to increase the allocation and things like that?
So let's see. It does have some defaults in there. I have had some code in there at some stage. I'm trying to remember if there's a CPP, like a Haxe API to be able to set the initial allocation. But currently what it does is it'll expand as it needs more and expands in blocks that you currently can't change that. And then it gets to a point, it actually, as I said, it does have the moving GC in there, or can have it, which actually can then reduce the number of blocks as well. So you can actually give up blocks of GC. But yeah, currently I'd have to reinvestigate that, because as I said, I have had stuff in there to do exactly that, but I don't think I've exposed it properly yet.
So I think, yeah, that was kind of like a hot issue for us a couple of years ago when we wanted to integrate the compiled code to other libraries and to a different application, and there you will get this issue that how you make sure it doesn't starve you or the other parts of the application, so you can reclaim like the memory that the Haxe module uses in a bigger application. So I would love to see things like that.
Especially if you're finally detaching from... I've added some new code in there actually for this scenario where you want to attach to the HXCPP system from one thread, do a little bit of work, then detach from it, and then carry on. I actually have to make use of this in the Android target now, where if an Android window dies, it actually, the thread dies with it and you get an attachment from another thread. So I've had to make it robust to having threads attach and detach from the GC system. And once you've detached all your threads, I guess, doing some kind of external compress should be quite efficient, because you know that nothing's being used. So yeah, something that could be certainly added easily enough. Yep.
Yeah, I guess you should come over here.
Sorry. It's very loud now. Is that okay? Thanks for the run through on the magic. It's very cool, the levels. All the magic you're talking about is kind of leaving Hex to go to native. Have you ever thought about going the other way? Like we're looking at using Hex to build libraries, and then the outer loop is native code. And we use the Hex code for some functionality that's really nice to build in Hex, where you have lots of cool technology, but then maybe we attach it to a native program. And part of the problem with HXCPP compared to, say, some of the other backends is the mapping to the native language is complicated, the way it nests classes and names them, and the object wrapping for smart pointers and things like this. So to write native code against that is a complicated task, and it's not even clear that that API would be stable if you were to build something on it. I mean, I guess you could build a layer to protect yourself, but I'm just curious if you thought, I don't know if that's black magic or what it is. It's the opposite kind of magic.
Yeah, that's true. So in some ways, Android target does use it in reverse, like the Java is running the main loop and is calling enemy to do the rendering. But they are really calling static functions, I guess. If you call static functions, a lot of those issues just disappear. You know, that you put a class in a package in your Haxe code, you have to type that package name when you use your static function. I think that's fair enough. We do also do a lot of stuff with the kind of reverse from within the native code. There's a class which is AutoGCRoot, which is a pointer to hold a pointer to the class, and therefore you can hold on to an object. And once you've got that object, just using the arrow notation on it will work, you know, quite naturally. But you need to, as you say, include the header file. Now, given that the header file is generated, and if you're going to need to have a dependency so that if that header file changes, then so that you have to recompile your CPP code. But that should work. And as I said, you've got to think about how the threads go. So one possibility is to enter the HXCPP library and then exit it back into your normal code, and then you'll be in a Haxe thread. The other one is to attach temporarily to the runtime. Then you can call your functions and then detach. So it is quite possible to do. It's just not well documented. And then so maybe that's the next step there. And I noticed the new Haxe site's big on documentation, so hopefully we get a bit more action there as well.
Just a small comment. I'm looking forward to have this all documented on the new website. That's all. Soon, I hope.
Okay, thank you very much, Hugh. Thank you.